Hello everyone, welcome to the NN Classroom. Today I'd like to share with you a past paper, question number 13, about the topic 14, bonding and structure in the higher level syllabus, related in 2017 time zone 0, November paper. Let's see. What is the hybridization state and the electron domain geometry? Here comes two very specific keywords. The first word is the hybridization state, and secondly is the electron domain geometry. Both are actually counting on, remind you, only the total electron domain number. But not the combinations of any of the bonding domain or lone pair electrons, right? Because electron domain geometry is different from the molecular geometry. Electron domain geometry, regardless of whether the electron domain is going to be a bonding area or a lone pair area, still counted as the geometry consideration. So that's why it is meaningless for us to count whether this, let's say, 4 domain is going to be 4 plus 0, 3 plus 1, or 2 plus 2. If you know what I'm saying, I'll be happy about that, right? If not, then try our lessons, right? So here comes meaning the electron domain geometry is going to be easier. We only need to count the total electron domain number, regardless of whether it is going to be a bonding domain or lone pair electrons, right? And so same idea as the hybridization state, because as we learn, for the 4 domain situation, we will having a sp3 hybridization, 3 domain number always sp2, and 2 domain number is going to be sp, right? And so from this perspective, around the circle elements of C, N, and O, right? So here comes to the structural formula given. Remind you that every time when the question just gives you the structural formula, don't forget to think of whether there is going to be some lone pair electrons, because lone pair electron, each pair count as 1 domain to the total, right? So that's why really carefully consider it. For this case, you can see carbon is going to be having 3 individual bonds, each to 1 hydrogen, and 1 bond to nitrogen. So that's why it is going to be a 4 domain situation, and all the 4 electrons are being used to form covalent bond. So that's why no lone pair, right? So if it's a 4 domain situation, we will be having a sp3 hybridization, and regardless of how many lone pair bond pair combination, electron domain geometry will be 4. In 4 situation will be always be tetrahedral. So that's why for the first choice, what we can select is only be A or C, right? For the next one, oxygen. This case, very careful. In the case of this oxygen, although true that oxygen normally forms a double bond or 2 single bonds, but remind you that the oxygen is going to be having 2 of the lone pair electrons left. As you can see, 6 electrons around the outermost shell. 2 of them used to form bonds, still remaining 4. 4 means 2 pairs, right? So for this perspective, what we can deduce is altogether 3 domain, right? 1 of the bonding domain, 2 lone pairs, each pair as 1 domain. So altogether 3 domain. In a 3 domain situation, we will be achieving sp2 hybridization in order to have the 3 domain to be used, right? And finally, the shape will be trigonal planar. For any of the 3 domain situation, the basic electron domain geometry is going to be trigonal planar. So that's why I confirm our choice, very high chance to be A, right? Let's see for the final element, which is going to be nitrogen, right? So in this case of nitrogen, you can see altogether 3 bonds are being formed, 1 double and 1 single, right? So count the electrons so carefully, you realize still having 1 lone pair, right? Because 5 electrons around outermost shell of nitrogen, 3 of them being used to form covalent bonds, so remain 1 lone pair, right? So altogether, totally we're having 1, 2, 3, also 3 domains, right? So totally 3 domains, same as sp2 hybridization, and the electron domain geometry is still going to be trigonal planar, right? So that's why obviously the answer is going to be A. One more time remind you is that what we are finding in this case is electron domain geometry, and electron domain geometry is going to be different from our real molecular geometry. So that's why although you may see that this oxygen and this nitrogen seems they're both having a different shape arrangement, but eventually in terms of electron domain geometry, both having 3 domains around the center, both should achieving the same electron domain geometry. So that's our answer for this case A.